Welcome back, everybody. This is our video solution to problem 4 from Quiz 12, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. In this problem, we are given a real operator t, and we're asked to find its determinant using the eigenvalue definition. Now, the way we're given the operator is with the matrix, and so you might be tempted to just say, well, I know how to find the determinant of a 2 by 2 matrix. I multiply the diagonals in each direction and then subtract. So the determinant of m of t would just be 1 minus negative 6, which is equal to 7. All right, and of course this will equal the determinant of t. But we are told explicitly, use the eigenvalue definition. So it's important for us to know what that is going to be. So the determinant of t is equal to the product of the eigenvalues. And of course, the determinant of t is equal to the determinant of m of t, which will also be equal to the product of its eigenvalues. All right, no change there, because the eigenvalues for t and for m of t are the same. Okay, so we need to find the eigenvalues for m of t. So let's use our standard approach here, where I'm going to multiply, say, by e1, which is 1, 0. And so I'm just going to call this te1 here, and I know that would be the first column, which is 1, 2. And this list, 1, 0, and then 1, 2, is linearly independent. So I'm going to keep going and compute t squared of e1, which is easy. I multiply this matrix here. All right, there's my m of t. I multiply it by 1, 2. So let's see, I'm going to get 1 minus 6, which is negative 5. And then 2 plus 2 is 4. All right, so I now have 3 vectors. This has to be linearly dependent. So let's see, to get one copy of negative 5, 4, let's see, I'll need 2 copies of 2 to get 4. But that's going to give me 2 here, but I want to get negative 5, so I'm going to have to subtract 7 copies of 1. So it looks to me like t squared e1 is equal to 2e1 minus 7e1. Or putting this all on one side, we're going to get 0 is equal to t squared e1 minus 2te1 plus 7, and we'll insert the I in because now I can factor out this e1, and I'll get t squared minus 2t plus 7i applied to e1. Okay, well, you might notice that we already have this 7 here, which matches the 7 that we found using the 2 by 2 trick. Are we actually done? Well, in a sense, yes. We have found actually the 7, and we know that if we multiply together the eigenvalues, it actually should give you the constant term of this polynomial. But let's see what happens, right? Just to double check. When I try to factor this using the quadratic formula, what do we get? So we would get t minus, and we're going to have 2, and we'll have a plus and a minus, so let's make this the plus, the square root of 4 minus 28 over 2i. And then the other piece will be t minus, and we'll have 2 minus the square root of 4 minus 28 over 2i, all applied to e1. Okay, so we can simplify a little bit, and on top, let's see, 4 minus 28 is negative 24. We can factor a 4 out, which will out of the square root, which will give it a 2, and all these 2's are going to cancel, so we'll end up with 1 plus what's left over. Well, there's a square root of 6, and then there's still this negative. We can just make that into an I, so I don't need to make no fraction here. So 1 plus the square root of 6i times the identity. And then the same thing here, only it'll be 1 minus the square root of 6i times the identity, e1. And so we see from here that we're going to get 2 eigenvalues. So the eigenvalues of t are going to be precisely 1 plus the square root of 6i and 1 minus the square root of 6i. And the product of those two eigenvalues is, well, exactly going to be this 7. All right, nothing actually surprising about that. That's what happens when you factor a quadratic. The two roots that you get, their product will be the constant term of the original quadratic. Okay, and so this implies that the determinant of m of t, which is equal to the determinant of t, is equal to 7. And there we go. All right, we'll see you next time when we compute the determinant in a different way.